So I'm like, excuse me. Here we go. Get everybody up here. So this is going to be really important for today's lesson. Way back when we talked about proving triangles congruent, do you guys remember we learned 5 ways to prove triangles congruent? Does anybody remember? Last year, yes. Does anybody remember the 5 ways, or at least one of those 5 ways that we proved triangles congruent? Base angles was a theorem we used maybe to get to our final goal, but we had very good, Emerald. So side, side, side. I heard angle, angle, side. Not angle, side, side. What else am I missing? All right. So these are the 5 ways to prove triangles congruent. What's it mean if triangles are congruent? What's equal? Okay, all of their corresponding sides are congruent, and all of their corresponding angles are congruent. That doesn't mean that they're regular. It doesn't mean that all the sides are the same, right? Or that all the angles are the same. It just means that if I have 2 triangles, this angle A is going to be congruent to this angle B. But it doesn't mean all the angles are the same. This angle C might be congruent to this angle D, right? And this angle E might be congruent to this angle F. So when we're talking about triangles being congruent, it means all of their corresponding parts are congruent. This side's going to be congruent to this side congruent to this side congruent to this side. But we didn't need all of those to prove them congruent. We only needed one of these shortcuts, right? And then we wrote what was called a congruence statement back when we did that. And this was an example of a congruence statement. All right, and when you wrote that congruent statement, what did it mean about the first 2 letters that were written down? They're congruent. Their angles are going to have the same measure. So where you put them mattered. You couldn't just name them any way you wanted. So this says identify the pairs of congruent angles and the pairs of congruent sides. And I saw a couple people, they were drawing pictures and labeling their pictures. That's so helpful if you need that visual. So draw yourself a picture of a triangle. Label it QRS. Draw yourself a picture of another triangle. In the same location, label it ZYX. And then you're going to list all the congruent corresponding parts. So let's start with the, oops, not ZYZ. Sorry. How about ZYX? So let's do the angles first. So let's go with Ruben. Give me one pair of angles that are congruent. Exactly. So remember, correct notation, we would put angle Q is congruent to angle Z. We would not put the little m. That's if we're giving its measurement, like 30 degrees. Okay, Andy, what's another pair of angles? Okay, and we can use 3 letters, but we don't have to. Since there's only one angle at every vertex, we can make it simple and just use 1 letter. So name 2 angles that would match up besides Q and Z. Very good. So we would say angle X is congruent to angle S. And then the last 2 angles, anybody? Angle R is congruent to angle Y. This is what I would be looking for if it says list the corresponding angles that are congruent. Okay, now let's do our sides. So Peyton, give me a pair of corresponding congruent sides. Okay, so remember when you name those sides, you're going to put a line segment above them. QR is congruent to ZY. Another pair of corresponding sides. Very good, Matt. RS is congruent to YX. And the last pair? Very good. SQ is congruent to XZ. You do not really have to have a picture to do that, though. You can just look at the congruent statement. It's telling you Q and Z match up, R and Y match up, S and X match up. And then the side links, the same thing. QR matches up with ZY, and so forth. You could keep doing that for every two letters. Does that make sense? Okay, the reason we're reviewing that, this is not new today, the reason we're reviewing that is because what we're going to learn today is the concept of similar, not congruent, but similar polygons. And what that looks like and what does that mean and what we're going to write today are what are called similarity statements, which will be very similar to a congruent statement. Okay, so it's going to be important that you understand kind of how that's related. All right, solving proportions. I told you a few minutes ago, this is probably the skill that you're going to use the most this week and next week, is solving a proportion. Back in middle school somewhere, you should have talked about the concept of what is a proportion versus what is a fraction. This is a fraction, right? This is a fraction. When you set a fraction equal to a fraction, that becomes a proportion. That's what a proportion is. A proportion is when one fraction equals another fraction. One way to solve a proportion is to simply just cross multiply. Sorry, my thing doesn't want to work today for some reason. I don't know what's going on. Let's see if my clicker will work. Maybe. I'll let you know when we get a little bit further in. Not today, okay? Okay, I don't know why it's not working. So, maybe it will now. I don't know, it doesn't like me. Maybe it's because I have my pen in my hand. Oh well, so what's trying to do is circle that. So I'm just going to write it over here on the whiteboard so you can see. So one more time, this is 2 over x minus 3 equals 8 over 3x minus 3. To solve a proportion, we're going to use the easy way here, which is just to cross multiply. Your Algebra 2 teachers may teach you a different way that you can solve that proportion. They'll talk about multiplying both sides maybe by x minus 3. And then multiplying both sides by 3x minus 3. But to me, it's a little easier at this point, at the level that we're learning, to just say cross multiply. Okay? So when we do that, there was some conversations around the room about, well, how do you know which one gets put in the parentheses? You use parentheses when you have more than one term that you're going to be multiplying by. So I need to do 2 times all of 3x minus 3. Set that equal to 8 times all of x minus 3. And then what do we do from there? So by multiply, you mean distribute. So we're going to distribute. What do we get here? And then here. All right. And then what do I do from here? Add 6. So 6x equals 8x minus 18. Is that right? Subtract 8x. Negative 2x equals negative 18. So when we divide by negative 2, what do we get for x? Positive 9. That's your answer. When it says solve a proportion, it means find the value of x. So when you find this answer, some of you said, well, do I need to plug it back in? Need to? No. Might want to, because then it just makes sure you did it correctly. If I plug this back in, I'm going to have 2 over 9 minus 3. What is 9 minus 3? 6. So this becomes 2 over 6, which reduces to 1/3. If I plug it in over here, I'm going to have 8 over 3 times 9 minus 3. What's 3 times 9? Minus 3. So this is 8 over 24, which reduces to 1/3. If you did it correctly, your fraction should be equal. Does that make sense? Okay, so you could plug it in just to double check you did it right, but you don't have to plug it in, okay? Your answer is what you get for x. Back in Algebra 1, you may have had a teacher that made you check your answers every time when you solved an equation just to get you really good at making sure you did it right. Okay, same thing on this one. I'm not going to take the time to work this all the way out because it's the same process. Did anybody get an answer here for x? Michael? Negative 18. Did anybody else get the same answer? Angelina, different? Positive 18. Anybody else? Something different? Okay, so maybe I will work this since we're getting different answers. All right, I'm going to work it on the board over here. So if you're watching the video, you can look at the filled-in notes because I'm going to work this over here on the whiteboard. All right, I have x minus 6 over 42 equals 2x minus 14 over 77. So remember, you're going to cross multiply. So you're going to take 77 times what? X minus 6. And that's going to be equal to 42 times 2x minus 14. Then you're going to distribute. We get 77x minus what? Help me out. 462. Okay. Equals 42 times 2x is 84x. And what's 42 times negative 14? Negative 588. Then we're going to subtract. I would probably move my 77x over here, which gives us negative 462 equals positive 7x minus 588. And then add your 588 to the other side, which is going to give you a positive 126. Is that correct? Equals 7x. And then divide by 7. And so x goes into 12 one time with 5 left over. 7 goes into 56 8 times. So we get positive 18. Questions on that one? All right, so be really careful with your signs and what you're writing down so you don't have little mistakes, because we're going to be doing that all chapter long. Cross multiplying. I'm going to have to fix this. Give me just a second. Talk amongst yourselves. Okay. Okay, we're good. Back in action. So, Chapter 7 is all about similar polygons. So we're going to relate this back to what we did a few chapters ago as well when we were proving triangles congruent. I need you guys to think just a little bit way back, Chapter 4. We started Chapter 4 by proving triangles were congruent without these shortcuts. Do you guys remember that we first proved triangles congruent by reflecting them, translating them, and rotating them? And we tried to make one triangle land on top of another triangle. And if we could flip it, slide it, or turn it to make it land on top of it, then we said they had to be congruent. It was section 4.1. It was the very first thing we did in chapter 4. And then we said, okay, besides transforming them to make them land on top of each other, we can prove it with two-column proofs. And that's when we got into these shortcuts. Okay? But the first thing we did was not proofs. It was on a graph, can I make this triangle land on top of this triangle? So we're going to kind of approach similar polygons the same way today. Instead of writing two-column proofs, we're going to be trying to figure out how can I make this triangle land on top of this triangle, or this circle land on top of this circle. So not just focusing on triangles today. But the difference is they're not going to be congruent, they're going to be similar. Meaning that one shape's going to be bigger or smaller than the other one. What transformation did we not use when we were doing congruent triangles? What transformation makes something bigger or smaller? Dilations. And so today we're going to review dilations, which is why in the second section of notes you had those transformation rules on the second warm-up. Okay? So we're kind of relating that idea of congruent figures now to making them bigger or smaller. All right. So first thing you need to know is what does it mean to be similar? I kind of gave you an idea just now. And also what can we do so we don't have to write the word similar every time? This little symbol means similar. What does that look like? A little squiggly, which we've been putting on the top of an equal sign to mean congruence. So now we're not saying they're equal, we're not saying they're congruent, but we're using the top part of that to say they're similar. Similar means they're going to be the same shape. You can't start out with a triangle and then end up with a rectangle. If you do, you've done something way wrong, okay? For them to be similar, they have to be the same shape, but they're going to get bigger or smaller. So they're not necessarily the same size. However, congruent triangles are similar. They are similar, but similar triangles are not necessarily congruent. Okay, so we're going to talk about that in a minute. All right, so here's just an example in your notes you'll see. These two triangles, when I look at triangle 1 and triangle 2, they are similar. You can tell triangle 1 looks just like triangle 2, but it's just gotten bigger. Whereas when you look at these triangles, do you agree that this looks almost like a right angle here? But does this triangle have a right angle? No. So my triangle that's not a right triangle can't turn into a right triangle. They have to stay the same shape, just get bigger or smaller. So this one is not similar to each other. All right. So here's your definition for similar polygons. This is very important. For two polygons, no matter what they are, for two polygons to be similar, there's two things that need to be true about them. And we're going to go over and over this chapter. Number one, their corresponding angles must be congruent. Their corresponding angles have to be congruent. That's the same as when we had congruent figures. Their corresponding angles had to be congruent. The difference is today we're talking about shapes that are going to get bigger or smaller. When you think of a blueprint, I don't know how many of you guys have ever seen a blueprint of a house or looked at something like that, but when you have a blueprint of a house, would you agree that the wall and the floor make a 90-degree angle on the blueprint? And then hopefully when they build the house, the wall and the floor still make a 90-degree angle, right? But the house is hopefully not the same size as the blueprint. The blueprint's going to be maybe an inch of length for the wall or 2 inches for the wall. You want your house to be maybe 10 feet or 9 feet or something like that. So the angles are going to stay congruent when you get bigger or smaller. Are the sides going to stay congruent? When your shapes get bigger or smaller, do the side lengths stay congruent? No. The side lengths are not going to be congruent. That's why they're not going to be congruent shapes. The second thing that's going to be true is their corresponding side lengths are going to be what we call proportional. There's that word again. What is a proportion? A fraction equals a fraction. What this means is they're not necessarily going to be the same size, but when you compare their side lengths, so for example, I want to show you up here what this word proportional means so that you can really understand. When I look at these two shapes, we're going to compare two sides to a different two corresponding sides. So let's start with AD. You may want to write this down. What side is AD going to match up with? EH. And again, here's this little similarity statement. You may want to write that on your notes as well. This is called the similarity statement. Notice that little similar symbol. Again, it looks similar to things we've done before, but it's not the same. Little squiggly. You can use the statement to match up your sides, or if you can tell by the angle measures, that's fine too. But this is always your go-to. We know that AD is going to match up with EH. Okay, so I'm going to compare these two corresponding sides to another two corresponding sides. So let's say AB. What is AB going to match up with? AB matches up with EF. Okay, let's plug in their numbers. So what's the length from A to D? 5. What's the length from E to H? 10. What's AB? 6. And what is EF? 12. Now reduce those. What is 5 over 10? 1/2. What is 6 over 12? 1/2. So what we're going to notice is the sides don't stay the same. They get bigger or smaller. But when you compare two corresponding sides, the fraction that they reduce to should be the same no matter which corresponding sides you match up. So 6 over 12 is 1/2. What's 4 over 8? 1/2. What's 5.4 over 10.8? 1/2. If they're similar, their side lengths have to be proportional, which means when you compare two sides and another two sides, they have to reduce to the same fraction. Does that make sense what I mean by proportional? Not equal. They're not going to be equal. They're going to be proportional. The angles will be equal, but not the sides. Okay? Again, this is called a similarity statement. If they ask you to write it, you're just naming the two shapes, making sure you're matching up the correct angles when you name them. You do not put a congruence symbol, you put a similarity symbol. Then just like the bell work, if they ask you to name the corresponding congruent angles, this is how you would name them, just like we did in the bell work. Match up the angles that match up. This is different right here. So I want us to practice doing this. This is listing the corresponding sides. So this would be listing the corresponding sides. This would be listing the corresponding angles. And every year I have students who miss this question because they're not paying close enough attention right now. So make sure you're following me. When it says list the corresponding sides, you are not going to say that they're equal to each other. You are going to say that one side over, making a fraction, over its corresponding side is equal to another two corresponding sides as a fraction equals another two corresponding sides as a fraction. You're going to do that for every pair of sides. Okay, so you're writing an extended proportion. The only thing that matters is that the same shape is on the top or the same shape is on the bottom. But as far as which order you go in, that doesn't matter at all. Okay? This little number right here is separate. It does not really go with listing the corresponding sides. This number, add this to your notes, is called the similarity ratio. Similarity ratio. It is what all of the sides reduce to. When you compare the corresponding sides, what fraction did we get every single time? 1/2. So that's what we call our similarity ratio. That means this figure is similar to this figure in a ratio of 1 to 2. So what does that mean the size of this is compared to this smaller one? Oops, sorry. Say it again, Tate. One more time. Twice its size. This is 2 times the measure of this one. So what does it mean this little one is compared to this big one? Half its size. Okay? So when you're looking at that similarity ratio, it's telling you how are they related? How much bigger or smaller did it get? Here's the part also that a lot of students make a mistake on. Your similarity ratio needs to match your figure. So whichever one you put first in your statement needs to go on top in your fraction. So if I say ABCD is similar to EFGH, then ABCD needs to be the numbers I put on the top. I'm going to say that again. Whichever one's named first has to go on top in your fraction. Otherwise, you're going to say that this one relates to this one, and if you flip it over, it's going to be a ratio of 2 to 1. But this shape is not 2 times this shape, right? So you need your ratio to make sense to what you said. So this shape compared to this shape is in the ratio of 1 to 2. All right, we're going to practice. I'm going to make sure you can do all of those things. So here's where that's all listed. Again, the similarity ratio is the number. And they're going to repeat one more time in this slide. If you put ABC to DEF, then 3 over 6 becomes 1 to 2. So ABC to DEF, 3 over 6, becomes 1 to 2. If you switch the order, DEF to ABC, then you have 6 over 3, which is 2 to 1. And you can write it either way, you just have to be consistent. Whichever one you put first has to go on top. Okay? I already said this as well, so if you flip it over, writing a similarity statement is like writing a congruent statement. Be sure to list your corresponding angles or vertices in the same order. When you write a similarity statement like triangle, ABC is similar to triangle, the angles have to match up. So whatever the next triangle's name is, make sure you're saying that these angles are congruent, these angles are congruent, and these angles are congruent. Okay, I don't think I put this one in your notes. Is that correct? Okay, so right now in that little blank spot that you have in the corner, I want you to write down at least these two pictures. Just draw these two pictures. I felt like we needed an extra practice problem, so I added one. Okay, so the question says, determine whether the polygons are similar. So one more time I'm going to ask you, what are the two things that have to be true for our shapes to be similar? Number one, what are we checking for? Look back at your Okay, they do have to be the same shape, yes. Back to your definition of similar, though, once you know you have the same shape. Reese? What about the corresponding angles? Congruent. So the first thing we have to check is, do we have congruent corresponding angles? This is huge. You have to have this memorized. What does it mean to be similar? Number one, corresponding angles have to be congruent. They tell you that these two shapes are what? Rectangles. What do we know from last chapter about rectangles and their angles? They all have four right angles, right? So would we agree that every corresponding angle in this rectangle will be congruent to every corresponding angle in the other rectangle? Okay, because they have four right angles, so that is true. Second thing, to be similar, what has to be true? Okay, the sides that correspond have to be proportional. Again, I worry about you understanding what that means, proportional. So remember, proportional means you're going to write two sides as a fraction and then another two sides as a fraction. And they should reduce to the same fraction. So we're going to compare our corresponding sides. Now, do I know which sides to match up if I don't know yet if these are similar? No. But what I can do is I know if they're going to be similar, that the bigger sides have to match up and the smaller sides have to match up, right? So when I look at my picture, what's the smallest side over here? 6. What's the smallest side over here? 4. So I don't want to write 6 over 6 because that's not how they're going to correspond. The smaller and the smaller ones will match up and the bigger ones and the bigger ones will match up. So if you're not quite sure how do these match up, smaller to smaller, bigger to bigger, okay? What else do we know about these missing sides in these rectangles? I'll double check my email and see if they've mentioned anything. Yes, they have. At 9:30, guys, so you can go. Here, make sure you watch the rest of the video, okay? And here's the assignment. And then I'll send out a reminder and let you know when it's due. Oh, band kids, we didn't get an email about band. But you are leaving at 9:30 as well? Okay. That's fine. No, I believe you. Who else is in band? Corbin, Reese, Angelina, Corbin, Andy, Cheer, sorry. Ruben. All right. No. I think Okay, guys, again, if you're leaving, watch the end of the video. At this point, it's at 30 minutes. So fast forward to 30 minutes, watch the end of it, okay? That way you don't miss anything. Thank you, Matt. Bye. See you guys. Have a good weekend. Yeah. I'll see him at the pep rally, too. All right, I tell you what we're going to do. We're just going to finish section 7.1 and we'll stop since so many people left. So if I can have your attention for just a few more minutes, then I'll let you work on that first page of your assignment, okay? So let's finish up here. So congruent corresponding angles, sides have to be proportional. So we're going to double check. But what I was asking you was, what do I know about these opposite sides since it's a rectangle? They're congruent. So I know this is 9 and I know this is 6, right? And I know this is 6 and I know this is 4. All right, because it's a rectangle. Now we wouldn't know that if they didn't tell us some information. So now we're going to compare. So we're going to write 6 corresponds with what side again? 4. And we're checking to see. We don't know. We're checking to see, is that equal to, and then we're going to compare 2 more corresponding sides. That? And it doesn't matter. What's going to matter is when you write your similarity ratio and your similarity statement, and I'll talk about that in just a minute, okay? Right now we're just checking to see, does it reduce to the same fraction? All right, so 6 over 4, everybody with me? And then that we're checking to see if that matches up with what other 2 sides? 9 and 6, so 9 over 6. What is 6 over 4 reduced to? Okay, 2 goes into both. 2 goes into 6 3 times, and 2 goes into 4 2 times. What does 9 over 6 reduce to? 3 goes into 9 3 times. 3 goes into 6 2 times. So are these the same fraction? Yes. We would have to compare all 4 sides if they weren't the same. Does that make sense? So if this was not a rectangle, we would have to check the next pair and the next pair. But we already know 6 over 4 is 3 halves. 9 over 6 is 3 halves. So are all corresponding sides proportional? Yes. Okay, so if they're similar, then you're going to answer the next part of the question. Write the similarity ratio, write the similarity statement. So when we write it, this is where it matters. You can decide which rectangle you want to name first. It won't matter. What will matter is how you write your similarity ratio. Whichever number you put on top, if that's your similarity ratio, 3 to 2, that's the one that has to come first when you name it. So Emerald, which one of these rectangles do you want to name first? Okay, so she said A, B, C, D needs to be similar to, and be careful that you write it so that they match up correctly. What is AB matching up with? EF. So make sure that you start the same location. So E, F, what? G, H. Okay, this is your similarity statement. If you name it this way, Emerald put A, B, C, D first. So that means these sides have to be the ones that went on top, which is what we did. And so what's our similarity ratio? What is this? What's the number that gives us the relationship? 3 over 2. A reduced version of what we got when we compared our sides. So this is our similarity ratio. This is the statement. This is the ratio. Are you guys with me on the difference? Similarity statement, similarity ratio. Now, what if we named it different? So let's say that Haley named it EFGH was similar to ABCD. What's going to change for our similarity ratio? 2/3, because now these sides have to go on top, which means we're flipping these over. Instead of being 6 to 4, we're doing 4 to 6. So this would be 2/3 as our similarity ratio. Are you understanding what I mean by whichever one's named first has to go on top? And your ratio needs to be reduced. Don't tell me that it's 6-4 or 9-6. Reduce it. Any questions on that one? Okay, look at the next one in your notes that was in there. It says determine whether polygons are similar. If so, write the similarity ratio and the similarity statement. If you look at these two, first of all, we need to know all corresponding sides and all corresponding angles. Do we know what angles P and R are? Do we know these values right now? No, but what kind of triangle is this? Isosceles. If it's isosceles, what did we learn back last semester about these base angles? They're congruent. Could we find these angles then if we know this is 36? How? 180 minus 36. That's going to give us the sum of these two, which would be what? 144. And then Tate said since they're the same, we would take 144 and divide it by 2. And we get 72 degrees. Okay, remind me one more time. For two shapes to be similar, their corresponding angles have to be what? Congruent. Right now, if I stop right here, are any of these angles going to match up with 62 degrees? No. I could find these missing angles as well because this shape's also isosceles. But as soon as I realize they're not going to be congruent, do I need to go any further? No. So are these polygons similar? No. So we're going to put not similar. And therefore, we can't write a similarity statement and we can't write a similarity ratio because they're not similar. Okay, that's why I added a second example because these weren't similar, so we needed to see how to do it if they were similar. All right, last example is where you can see how this relates to a real life application. Why would we need to talk about similarity? Anything you see in life that is a scaled version of something else. If you have ever bought a Statue of Liberty little keychain, sure. If it's really, truly scaled down version, then that means it's got some relationship between the real Statue of Liberty and your scaled down keychain version. They should have some similarity ratio, some ratio of maybe 1 to 150, who knows. Same thing with a model car. If you have a little model car that you've had as a kid, and then you have a real car, if it's really a scaled version of that car, it's got a similarity ratio, okay? And so that's what this is all about. So it says find the length of the model to the nearest tenth of a centimeter. If it's a model, they are telling you that the two shapes are similar. When they talk about model cars or model airplanes, they're similar. They have been created with the exact ratio. So if they're similar, what we can do is write a proportion. And then we can solve it. So what we need to do is write a proportion by comparing our corresponding sides. Same units. You don't have to have the same units when you're doing a proportion as long as you have the same units, like the shape has all the same units. And this shape has all the same units. So if this one's in meters and this one's in centimeters, it's still going to work out to write a proportion. What you couldn't do is have, for example, let's say that it was me and my shadow. I can't say that I am 5 foot 6 inches. That's two different units. I would need to either quote my height all in terms of feet or all in terms of inches. But your two different shapes can have different units, and that's okay. And I'll show you why when we write it down, okay? So let's compare our sides, and we're going to write a proportion. So what side will 1.8 meters match up with? 6.3 centimeters. So we're going to write that as a fraction. 1.8 meters matches up with 6.3 centimeters. We're just comparing two sides, if you would, of our shape. Okay, which means the 5 meters is going to match up with X. What you want to make sure when you write your proportion is that you keep your shape in the same location. So if I'm talking about this racing car on the top, keep it on the top. If I'm talking about the model on the bottom, keep it on the bottom. Okay, once you do that, then you can just cross multiply like we did in the bell work. When you cross multiply, you're going to get x times what? 1.8 what? Meters. I'm going to keep my units in here to show you why it works out. Equals, now we're going to multiply what? 5 meters times 6.3 centimeters. Okay, go ahead and do 5 times 6.3 and tell me what you get. Okay, I want you to watch the units up here on the board. This is 1.8 times x meters, and this is 31.5 meters times centimeters, right? We've got both units over there. So what are we going to do here to solve for x? If we want to get x by itself, what do we need to do? Okay, we're going to need to divide by meters. What else are we going to need to divide by? 1.8. We need to get x by itself, so we're going to divide by 1.8 meters on both sides. What's going to happen to the meters on the left? Cancel, and the 1.8 cancels, right? What's going to happen to the meters on the right? They cancel. And what is 31.5 divided by 1.8? To the nearest tenth, 17.5. Okay, so 17.5, and then what units are we left with? Centimeters, which we didn't really have to do all of that with our units because we know that the model is going to be measured in centimeters. But to show you why you can have different units, it ends up canceling out and it works out anyway. Questions? All right, so we'll just stop